In this video, we're going to be covering section 7-2, estimating a population mean. So I want to start with kind of explaining or going over the an overview of what's going on. So the purpose of estimating a population mean is we want to find out the mean of a population. So for example, let's just say that the population we're dealing with or we're interested in is California. So the households of California. And let's say we want to know, or we want to estimate, or the mean. So we want to know about the population mean household income for all of Californians. Well, there's a difficulty with figuring that out because according to the 2000 census, there's approximately 11.5 million households in California. So if we want to survey everyone, it's going to be a little bit tough to do that, right? There's too many households. So instead, we take a sample, right? We're going to take a random sample of, say, and I'm just going to make up the number here, say like 500 households in California. And from there, we're going to get the household income from each of these 500 houses. And what we get is we can calculate the sample mean income for those 500 households. So X bar, and I'll just write it below here. So X bar represents the sample mean income, household income. Oops. Okay, and let's just say, for example, that number was 60,000 for, just to make this a simple example, right? So this is our best estimate for mu, which is the population mean. So we call this, so in this example, in estimating a population mean, this is the best point estimate. The sample mean is the best point estimate for the population mean. And similar to the previous section, there's probably an error. There's an error to our estimation because this is only a sample of 500 households out of many, many, many households, right? So we need a margin of error. So let's just say that after calculating or taking all of this into account, by taking all of this into account, what I mean is we also need to know the standard deviation. So let's just say that the sample standard deviation was, I don't know, like $10,000, right? And then we also need a confidence level. So the confidence level, we want a confidence level of, say, 95%. So after taking all of this into account, we can calculate a margin of error. So let's just say the margin of error is $879. So with the best point estimate and along with the margin of error, we can construct a confidence interval, right? So what a confidence interval is, again, we abbreviate confidence. You're going to see me abbreviate confidence interval as CI. What a confidence interval is it's our estimation of the population mean household income for California for this example. And we can write it in three different forms, right? We can write it in the plus minus form. Again, this is not like an official name. This is what I named it. And the plus minus form would be like 60,000 plus or minus the margin of error. So in this case, 879. Go ahead and put the dollar signs there. All right, so this is the plus minus form, and the format or the structure of it is X bar plus or minus the margin of error, right? And then we also have two other forms. The first one is the inequality form, or the other one, the next one is the inequality form, and that can be obtained by getting our lower and an upper, right? And our lower is just the X bar minus the margin of error, and then the upper is the X bar plus the margin of error. And this is how we would write it, right? So this is our kind of our lower bound, and this is our upper bound. And what we're saying with this notation is that the population mean household income for Californians is anywhere between this number 59,121 and 60,879. And that we're 95% confident of that the actual true population mean household income is between those two numbers. And then the third way that we can write this confidence interval is as an interval notation. Interval notation. And interval notation is just a math notation where we have, we're going to have a parentheses because this less than sign means that it's inclusive. So it's not including this value. And then comma, so this is lower, comma, upper. So the upper is 60,879. And let me just delete these commas just so that it doesn't look confusing. So we would just put down, we would write down the lower bound, comma, the upper bound, just like that. All right, so again, this should look very familiar to you guys, right? It's pretty much the same thing as what we did in the previous section, but now instead of dealing with population proportion, we're dealing with population mean. So these are some notations that you must be familiar with. The population mean, right? That's something that you've seen before. The sample mean, the population standard deviation. Lowercase s is the sample standard deviation. N is a number of sample or sample size. Capital E is the margin of error. This is a new notation or a new term that you need to know. DF, whenever you see DF, that's me representing this concept or this thing called the degrees of freedom. We'll talk about that more later in a bit. And in this section, the degrees of freedom is equal to n minus 1. These are the three ways that you can represent a confidence interval. Confidence level we've talked about already in this section. The confidence level is equal to 1 minus alpha, where alpha is the significance level. And likewise, alpha, or similarly, alpha is equal to 1 minus the confidence level. Again, that can be obtained by just rearranging the CL equals to 1 minus alpha. Okay, and then we talked about in previous videos about the critical z value, z sub alpha divided by 2. But this is something new. The critical t value is t sub alpha divided by 2. And I'll talk about that in a bit as well. Because we're going to be introduced to something called the t distribution. And let's go ahead and talk about that right now. So we talked about the z distribution, which is just the standard normal distribution, right? There's something called the t distribution as well. So the t distribution, I don't want to go into too much detail about it, but I'll link up into I'll link it in the description. I'll also put a link here if you want to know more about it. But essentially, what you need to know is that when sigma, the population standard deviation, is known, we use the z distribution. So we're in the z distribution when sigma is known. However, when sigma is not known, or so when sigma, the population standard deviation, is unknown, we're now in a different distribution called the t distribution. And the thing with the t distribution, just real briefly, is there's many different graphs that models whatever we're dealing with, and the different graphs, they refer to the degrees of freedom. So depending on the degrees of freedom, we get like many different graphs. And again, in this section for the t distribution, the degrees of freedom is n minus 1, where n is the sample size. All right. So these are formulas that you need to know as well. Just methods in figuring out the different values that you need to know how to find. So let's go ahead and jump right into some problems to see how to do the problems that you're going to be seeing in your homework. All right, so question 1, it's 3 parts. It says identify or calculate the sample mean. Then question B says determine which distribution is appropriate. Is it a z or a t distribution? Question C says construct and write the confidence interval in all 3 forms. So construct and write the confidence interval in all three forms. All right, so let's start with the first part for this problem. So this problem, it says, in a clinical trial for a diet pill, 58 adults took a diet pill for 6 months. Their mean weight loss at the end of 6 months was found to be 5.7 pounds, with a standard deviation of 4.2 pounds. Use a 90% confidence interval. All right, so question A says identify or calculate the sample mean. So in this problem, we don't need to calculate it because it's already given, right? So we just need to identify. So the sample mean, so in the sample of 58 adults, their mean weight loss was 5.7 pounds. So X bar is equal to 5.7 pounds. Question B says determine which distribution is appropriate. Z or T. So again, we're in the Z distribution if sigma is known. Otherwise, we're in this T distribution when sigma is unknown. So in this case, well, let's see. Just a reminder, this is a common mistake a lot of students make. You got to know that sigma represents the population standard deviation. And I'm just going to write that as pop standard dev. And then lowercase s represents the sample standard deviation, standard dev. Okay, so in this problem it says that their mean weight loss at the end of 6 months was found to be 5.7 pounds. So we know that's the sample mean with a standard deviation of 4.2 pounds. Now, what is this? This is a standard deviation, but is it sigma or is it s? The sample standard deviation. So is it population or is it the sample standard deviation? So because it says it follows from their mean weight, right? Talking about the sample of 58 adults, this is S. This is not sigma. So a lot of students, oops, this should have been X bar. So a lot of students make the mistake of seeing this with the word standard deviation and assuming that it's the population standard deviation. It's not the population standard deviation. In this problem, it's lowercase s, right? It's the sample. Okay, so now we know that we're in the T distribution. Again, if sigma is known, we're in the Z. Sigma is unknown, we're in the T. And usually we know that sigma is unknown if S is known. So if S is given, actually we'll just put that's better terminology. So if S is given, then we know that sigma is unknown. That's usually the case. All right, so now that goes to question C. So question C says construct and write the confidence interval in all three forms. So we're going to need to write it in the plus minus form. And then we're also going to need to write it as an inequality and then as an interval form. So let's go the easy route. There is a function on the calculator that would calculate this for you, right? So the function that in the calculator that would construct a confidence interval, it is either the T interval or the Z interval, depending on what distribution you're in. So because this is a T distribution, we're going to use the T interval function. All right, so you all should be familiar with where to find that. So it is, here's how you find it. You're going to press stat, you're going to go to tests, and then you're going to go to T interval. All right, so T interval to construct a T interval. We're given statistics. These values here are statistics. Okay, and then X bar is the sample mean, that's 5.7. S is 4.2. N is 58. Right, that's the sample size. And the confidence level here is 90% confidence level. So I'm going to put down 0.9 or 0.90. It doesn't matter. All right, so we're going to calculate. And the output that we get is in interval form. So I'm going to round to one decimal place as the instruction suggests. So in interval form, the confidence interval here would be 4.8 to 6.6. All right, so, and from here, from the interval form, it's very simple to get the inequality form, because the inequality form is, the format of it is just lower, less than the mean, less than the upper, right? Because again, the population mean, mu here, because we're dealing with population mean. All right, so the lower would be 4.8 pounds and the upper would be 6.6 pounds. And then finally, for the plus minus form, you need x bar plus or minus the margin of error. Okay, so x bar was given to us, so that's 5.7. Now we need the margin of error. So for the margin of error, so very similar to what the formula for the last section. Oh, there's a typo here actually. Actually, there's not. I apologize. These are correct. So the two minus signs here, because both of these are margin of error, depending on whether it's a t distribution or z distribution, right? So this is a t distribution because sigma is unknown. This is a z distribution. Okay, so we're going to use this formula, right? Upper minus lower divided by 2. Okay, so the margin of error here would be 6.6 minus 4.8 divided by 2. And one other thing, I've mentioned this before, put parentheses around your numerator just to remind you that when you put it into the calculator to put parentheses. Okay, so let's pull up the calculator and calculate that. So we're going to open up parentheses. That's going to be 6.6 minus 4.8 and then close parentheses. And then we're going to divide by 2. All right, so the margin of error would be let's keep it consistent with the green color, 0.9 pounds. Okay, so this is pretty much the majority of what you need to know in this section. You need to know how to calculate a constructed confidence interval and then convert it to all three forms. All right, let's go ahead and take a look at another problem. So before we look at number 2, let's look at number 3. So number 3, it says, in a survey of 35 randomly selected college professors, their mean salary, annual salary, was found to be $62,386. Given that the population standard deviation for annual salary for college professors is sigma equals 9,214, construct a confidence interval to estimate the mean annual salary for all college professors. Use a confidence level of 95%. All right, so following those, answering those 3 questions, so A would be what is the sample mean, right? So the sample mean in this problem would be the 62,386, right? It's given right here. There, meaning the sample of 35 randomly selected college professors, their mean annual salary is this much. So B is, we have to determine whether we're in the Z distribution or T distribution. Again, sigma known, we're in the Z, sigma unknown, we're in the T. So in this case, sigma is given. Sigma is the population standard deviation. So we're in the Z distribution. So then question C says, construct the confidence interval and write in all 3 forms. So we have the plus minus form, we have the inequality form, and we have the interval form. Okay, so the easiest one to obtain is the interval, because we know we can use the calculator for that. All right, so let's go ahead and go to the calculator. So we're gonna go to stat, go to tests, and we know this is going to be Z interval because it's a Z distribution and we're constructing an interval for population mean. So we're gonna press enter. We're given statistics. So the first input value is this population standard deviation, sigma. So that's going to be 9,214. And then X bar is 62,386. N is 35, right? 35 selected college professors. And the confidence level here is 0.95. Confidence level is 95%. All right, so press calculate. and it gives us a lower and an upper. And so this confidence interval is in interval form, right? So we have 59,333 as our lower, and then the upper is 65,439. And as an inequality, we have 59,333 less than mean, population mean, less than 65,439, right? So just like that. And then plus or minus form is x bar. So the x bar is that guy right there. So that's going to be 60,000, so 62,386 plus or minus the margin of error. So now we got to calculate the margin of error. And we know that the margin of error is the upper plus the lower divided by 2. I apologize. It's the upper minus the lower divided by 2. Okay, so let's go ahead and calculate that. So again, let me go ahead and just write it over here. So I'm going to write it up over here so you guys can see the math that I'm doing. So 65,439 minus 59,333 divided by 2. And again, always it's a good idea to put the parentheses there just to remind yourself to put it there when you put it into the calculator. Okay, so we're going to open parentheses, 65,439 minus 59,333, and then close parentheses, divide by 2. All right, so the margin of error is right there. So plus or minus 3,000, plus or minus 3,053. Okay, so what we're saying with the confidence interval is we're saying that the our estimation is anywhere between the population mean annual salary for all college professors is anywhere between 59,333 and 65,439. Or another way to say it is 62,386 plus or minus 3,053. All right, so let's go ahead and go to number 2. So number 2 is a little bit different. So number 2 says listed below are the number of years it took a random sample of adults to complete their bachelor's degree. So these are the number of years in a sample of however many people here. And this is the number of years that it took each individual in the sample to complete a bachelor's degree. Constructing 99% confidence interval estimate for the mean time required for all college students to complete a bachelor's degree. So let me just kind of take a step back to kind of explain what's going on. So we have a population, and our population is students who graduate from a college, right? There are millions of people who graduate from college. So it's very difficult to determine, and what we're interested in is the mean time that it took them to graduate, right? So the population, the mu here would represent the population mean time that it took a typical person, let's just say the population of the United States, for a U.S. student to graduate from college. So too many students who graduate, so we take a sample, right? So here's our sample, the data for our sample, and we want to estimate mu from this sample. So going back to the problem, so problem number 1 was we need to calculate x bar, and then problem number 2, or question B was, well, is this a z or t? Well, let's see. Let's calculate the x bar first. So let me show you guys how to do this. So when you're given a list of data, as opposed to being given like values, like statistics here, what you want to do is here's how you do it. So let me just go ahead and tell you. First of all, this is a t distribution. It's actually easier to just identify whether it's z or t. It's a t distribution because we know that because we're not given sigma. The population standard deviation is not given in the problem. So we know it's a t distribution. So we know we're going to use t-interval, but before we can use t-interval, when we're given a data set, we want to put that data set into a list in our calculator. So to do that, we're going to go to Stat, and then we're going to click Edit, and we're going to input it into L1. So let me go ahead and do that. Okay, so I put it into a list already. So the next step would be we want to run t interval on this list. So it's always a good idea to quit out of this screen. So we're gonna click second mode, and then go back to Stat, and then Test, and then go to t interval. So instead of selecting stats, we're gonna select data, and I stored this list in L1. So that's good, right? Let's just say that there wasn't a list there. To access L1, you would just press second 1. Frequency, we're going to leave as 1. Confidence level, we have to change that if it's different. So here, the confidence level is 99%. So we're going to click a 9 there, and then go down here and calculate. Okay, so we have several things. The first thing is for question A, it wants the X bar. So that's 5.9. years in this case. 5.9 years is the average for the sample for graduating from college with their bachelor's. And then this is my interval. This is my confidence interval. All right. So for question C, it was asking for the plus or minus form of a confidence interval, the inequality form, and then lastly the interval form. So with this problem, I'll just tell you that this is the interval form, right? So that is 3.5 is the lower, and then the upper is 8.3. All right, and then you should know how to do the inequality and then the plus or minus, right? So go ahead and do that as practice. For this video, for the purpose of this video, to shorten it, I'm going to move on to the next problem. All right, so for number 4 is a different type of problem. So what it's saying here is do one of the following as appropriate. Either find a critical t-value if it's a t distribution, or find a critical z-value for a z distribution. Round your answers to 2 decimal places. So if you look at our table here, we have for critical t-value, for using the calculator, method 1 is using the calculator for the z and t. You're going to use inverse t. And then for method 2 is you're going to use a table, a critical value table. For the purpose of this video, for critical z values, we'll use the inverse norm. For critical t value, I'll show you guys using inverse t and using the t critical value table. Those of you guys who have the TI-83 plus, you do not have this function, so you're going to have to use the t table. Okay. So going to this problem, so that's the first thing. We have to determine whether it's t or z, which distribution we're in, right? So for question A, it says we want to calculate a critical value for a confidence level of 95%, where n is equal to 40, sigma is equal to 2.7. So sigma is the population standard deviation. And it says the population appears to be normally distributed. So we know sigma, which means we're in the z distribution. So which means we need to figure out z sub alpha divided by 2. All right, so in this case, we're not given alpha, but we know that alpha for this problem, for these problem, is equal to 1 minus the confidence level. So for example, in this problem, question A, we know that alpha is equal to 1 minus 0.95, right? The confidence level is 95%. That's going to be 1 minus 0.95. So alpha is equal to 0.05. So alpha is equal to 0.05, which means we need to figure out this z sub 0.05 divided by 2. Okay, so in a prior video or in the prior section, if you guys recall, the way that we find this is we're going to do inverse norm. That's going to be 1 minus alpha divided by 2. So in this case, 0.05 divided by 2. The mean is 0, standard deviation is 1. So if you forget how we did this, this was in chapter 6, I want to say section 6.1 or 6.2, one of those sections. So go back and look at the notes there to get to see how you do this, right? But pretty much this is how you do it. You got to figure out, you got to know alpha first, and then just plug it in like that. All right, so let me show you guys how to punch that in. So to access inverse norm, that function is under the distribution functions. So we're going to press second vars, inverse norm. So in the area, we're going to put this value, right? This expression, 1 minus 0.05 divided by 2. And then the mean is 0, standard deviation is 1. Click paste, press enter, and there he is. So we get approximately 1.96. Rounded, again, we're rounding to 2 decimal places. Those of you guys who have the, what do you call it? The TI-83, I'll show you guys. Just as a reminder, you need to, you're going to get an output that looks like this, right? So you're not going to get the screen that we had with the other one, with the TI-84. So even some older 84, you're going to get this output. So you need to input the expressions with comma. So just like this, right? Divide by 2, and then comma, and 0, and then comma, and 1, and then close parentheses, right? Okay, so I'm changed back to the 84. Okay, so for question B, so we have a confidence level of 99%, n is equal to 52, s is 2.4, s is the sample standard deviation, population appears to be normally distributed. So we know that s is known, so which means sigma is unknown. So in that case, if sigma is unknown, then we're in the t distribution, which means we need to figure out t sub alpha divided by 2. So very similar to, well, let's just figure out what alpha is first, right? Alpha is equal to 1 minus the confidence level. So in this case, that's 1 minus 0.99, which makes alpha 0.01. Okay, so that we know. So let's kind of just write it down over here somewhere. So let me write it down here. So alpha is equal to 0.01. And then in addition to, with the t distribution, you need to figure out the degrees of freedom. So for t distribution, you need to figure out the degrees of freedom. And degrees of freedom for the t distribution is n minus 1. So that's in this case 52 minus 1. So degrees of freedom is 51. And for those of you guys who are using the table, you also need to know that anytime you're calculating the critical values t sub alpha divided by 2, you're in a two-tailed test. So for chapter 7, we're only dealing with two tails. So here, you need to know that we're dealing with two tails. Later on in chapter 8, when we see something like t sub alpha or like z sub alpha, whenever there's not that divide by 2, then that's telling you that it's a one-tailed test. All right. So kind of just keep these three things in mind, or these three things. You got to know these three things to figure out the critical value. So using the TI-84 calculator, where for those of you guys who have the TI-84 that has an inverse t, again, the TI-83 does not have this function. I believe some TI-84, the older ones, don't have this function as well. But those of you guys who do, you can use inverse t. You're going to need 3 inputs. So let me go ahead and navigate to inverse t. So we're going to press second vars, and we're going to go down to inverse t, which is the 4th function. So we need the area. So similar to when we were calculating the inverse, or the z sub, the critical z value, we put the same thing. So we're going to put 1 minus alpha 0.01, which is alpha in this problem, right? 0.01 divided by 2. And then the next input would be the degrees of freedom. So degrees of freedom is 51 in this problem. So let's go ahead and put all those 1 minus 0.01 divided by 2. And then degrees of freedom is 51. So paste. And we get that the critical t value is 2.68. Okay, so that's how you figure that out using the TI-84 function. So those who have the TI-83, you're going to have to use the critical t-value table. And this critical t-value table, for my students, you guys can you can find this table under the notes, under critical table folder. So again, you need to know three things. You need to know the degrees of freedom. So in this problem, if you guys remember, the degrees of freedom was 51. So we are in, notice how there's not a 51. You just have to choose the closest one, the closest degrees of freedom. So in this case, 51 is closest to 50. So we're in this row. And then you need to know whether it's a 2 tails, area in 2 tails, or 1 tail. It's 2 tails, right? It's 2 tails, 2 tail. And then you also need to know alpha is. So alpha is 0.01. So 0.01 is the first column. So essentially, you're in the first column, right? First column, this row. So the intersection of this row and this column would be that value right there. So 2.678. So 2.678. So we get, using the table, that's 2.678. And if you round to 2 decimal places, as the instruction suggested right here, then you get the same exact answer, right? The 7 becomes an 8. Okay, so that's how you figure out critical values, critical t values or critical z values. All right, and then lastly, let's take a look at the last problem. So the last type of problem you're going to see in this section is asking you to find the sample size required to estimate the population mean. So the problem here says find the sample size needed to estimate the mean starting salary for a computer engineer. We want a 95% confidence that the sample mean is within 4,500 of the population mean. And the population standard deviation, so sigma, is known to be 6,378. So lots of things that were given. Let's look at the table of values that we need to know how to calculate. So these are the values you must know how to calculate. And here we're in required sample size, right? So this is the formula for required sample size when we're trying to estimate a population mean. So very important that you understand this is the formula for required sample size for estimating a population mean. In the prior videos, in the prior section, there were 2 different formulas for required sample size for population proportion. So those are different formulas used for proportions. This is used for the mean. Okay, so let me just rewrite the formula here so we don't have to go back and forth. So we have the critical value times sigma divided by the margin of error, and then all of that squared. Okay, so now it's just a matter of finding each of the values, right? So for example, like the critical value here, for a problem like this where it's asking for the sample size for the critical value, if it's a common confidence level like 95%, which is one of those common confidence levels, use one of those values that I gave in the prior section. So in 6-1, or I'm sorry, in 7-1, there you had this table of common confidence level and their critical z values, right? So we have 3 common confidence levels that we use in this chapter: 90%, 95%, 99.99%. And these are the critical values for them, for the z sub alpha divided by 2 critical value. So these values don't change for this critical value. All right, so we're going to use one of those values, and believe it was like 95% confidence level. So we're going to use 1.96. Okay, so that's 1.96 for the critical value. And then we need sigma. So sigma was given to us as 6,378, right? Sigma is the population standard deviation. And then the margin of error. So the margin of error is the last value we need to know. And this is code word for margin of error. So within, the mean is within 4,500. That's code word for margin of error. Now, don't count on always seeing within, the word within, to determine your margin of error, but just know what the margin of error means, right? The margin of error is how far you're off. And essentially when it says we want 95% confidence that the sample mean is within 4,500 of the population mean. So within 45, let's just say this is the population mean, right? Within the population mean is telling us like plus this much plus that much. So this is plus the margin of error minus the margin of error, right? So essentially that is telling us that this is the margin of error, right? Within 4,500. Okay, so the margin of error is 4,500, and we're going to evaluate all of this, and then we're going to square it. So let me show you guys how I would put it into the calculator. Several ways you could do it, but here's one way. I'm going to evaluate what's inside first, and then once I get that value, then I'm going to square it. Okay, so let me show you how I'm going to do it. So I'm going to do 1.96. I could put parentheses if I like. I can multiply or just press the multiplication button. I'll just go ahead and put the parentheses. All right, and then close parentheses, and then divide, right? So divide by 4,500, press enter. And this is not my answer. I need to square it. So we're gonna need to square it. I can immediately press the square button here, or I can raise it. This is like the generic raise to the power, right? Raise to the second power. And then what happens is it's going to raise my answer, my previous answer by square, or by 2, by the second power. All right, so this is what I get. And with the sample size, you're always going to round up. So regardless of what the decimal number is, like regardless of what this is, as long as you get a decimal value, you're always going to round up to the nearest whole number. So this is going to be 8, right? So just kind of, I want to emphasize that. Like let's just say, for example, that the answer that you obtained was like 7. Let's go back here. So 7.1254. Your answer here is still going to be 8 if this was the output, right? Because you're always going to round up. Again, it's on your notes right here. Always round up to the nearest whole number. Okay, so that's the end of section of this video, and the end of section 7-2. Again, as always, please reach out if you have any questions.